Hello there, and welcome to the Sleepy Space Channel. Tonight, the unsettling, oddly quiet truth about one direction in space that humanity has barely ever entered: the vertical, straight up and straight down, out of the flat plane, the planets all share. Of all the images we have ever managed to take of the cosmos, the photograph, looking down at our own solar system from above, is still missing. The reason is not distance, and it is not engineering will. The reason is that the orbital motion every spacecraft inherits from the Earth makes climbing out of that plane harder than reaching Pluto. Over the next 2 hours, we will walk through why, what waits up there for any probe that ever makes the trip, and the strange dive toward the sun maneuver that may finally let one of them do it. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. There is a single quiet fact about the place we live that almost no one is taught directly, and yet it shapes every photograph of the sky we have ever made. Our solar system is not a sphere of orbits or a loose cloud of bodies. It is a disk, a wide, slowly turning, almost paper-thin disk of planets and moons and asteroids and comets, all swimming inside the same gentle plane, all bending around the same central star, all caught in the same long sideways motion that has held them for 4.5 billion years. The Sun is the still hub of that disk. The planets are the markers along its inner rings. And the direction perpendicular to that disk, the direction we casually think of as up or down, depending on which side you choose, is a direction in which almost nothing in our experience has ever moved. The flatness of the solar system is the most important geometric fact about where we are. It is also one of the most overlooked, because nearly every diagram we have ever seen of the planets has been drawn from the side, where the disk is obvious and unremarkable, or from above, where the disk is presented as the default and not as a strange architectural fact in its own right. Standing on Earth, the disk is everywhere. The sun rises and sets along a line. The moon follows that same line. The planets drift along it. Every familiar light in the night sky, except for the fixed stars far behind, moves along a single curve overhead, called the ecliptic. The ecliptic is the disk seen from inside it, traced as the line where everything we know how to find lives. The flatness is not a coincidence, and not a design choice. It is the fossil signature of how the solar system was born. The picture is one of the great calm ideas in modern astronomy, and it is worth giving the listener a few unhurried sentences to settle into. Imagine a slowly turning cloud of gas and dust, vastly wider than any solar system, drifting through interstellar space. Gravity inside the cloud pulls inward. Rotation, conserved as the cloud contracts, spins outward in the direction perpendicular to the spin axis. The cloud can collapse freely along its spin axis because nothing supports it there, but it cannot collapse across that axis without first shedding the rotation that holds it up. The contracting cloud, given enough time, flattens. The pole-to-pole direction collapses. The equator-to-equator direction holds. What was a cloud becomes a disk. A young sun forms at the disk's center, gathering the bulk of the material into a single hot core. Around it, the disk cools, and the heavier elements condense into solid grains. The grains stick. The growing clumps sweep up more material as they orbit. Planets accumulate in the plane of the disk, inheriting its geometry exactly. Anything that wanders too far above or below the plane is either pulled back into it by the disk's gravity, scattered outward and lost, or simply fails to assemble at all. Angular momentum, once acquired by the cloud, becomes the long sideways motion that keeps the disk spread out across light hours of space. The disk that the planets grew in is gone now, dispersed by the young sun's brightness, but the planets themselves remain in the plane, the disk once defined. The same principle plays out at every scale where rotation and gravity are present together. The rings of Saturn are a small disk. The disk of the Milky Way galaxy is a vast one. The accretion disks that feed material onto black holes are disks as well, made of the same physics, rotating, contracting, flattening, supporting themselves outward through angular momentum while collapsing freely along their poles. Flatness is what gravity plus rotation almost always produces. A spherical solar system would be the strange thing. A disk is the natural outcome. The plane the solar system settled into has a precise definition. It is called the invariable plane, and it is the average of all the planetary orbits, weighted by their angular momentum. The planet with the most angular momentum sets the strongest contribution, which is why Jupiter, as the most massive planet, weights the invariable plane heavily toward its own orbit. Earth's own orbit, the one the listener is currently riding on, is tilted by only about 1.5 degrees relative to the invariable plane. From a practical standpoint, this difference is small enough that the ecliptic, the plane of Earth's orbit, projected outward across the sky, is usually treated as if it were the plane of the solar system itself. Most of the major bodies in the solar system orbit within a few degrees of the ecliptic. Mercury, the innermost planet, tilts about 7 degrees. Venus and Mars and the gas giants are tilted by smaller amounts. Pluto, the most famous outlier, sits at about 17 degrees, which is enough to give its orbit a noticeable rise and fall above and below the plane. A handful of small icy bodies far beyond Neptune tilt more steeply still, and a few long-period comets arrive from random directions, plunging through the disk and out again. But these are decorations on a fundamentally flat system. The bulk of what orbits the Sun does so within a thin band of sky. The disk did not disappear when the planets formed. A diffuse residue of fine dust still hugs the plane, replenished slowly by the everyday processes of the solar system itself. Asteroid collisions, which happen quietly and continuously between Mars and Jupiter, grind small fragments into still smaller fragments, and eventually into micron-scale grains. Comets, when they pass close to the Sun, shed dust along their orbits. Far beyond Neptune, the slow erosion of icy bodies adds a faint contribution from the outer edges of the system. All of this dust collects in the plane, because everything that produces it lives in the plane, and the Sun's radiation pressure and the planet's gravity keep it there. The result is a thin, faintly luminous disk of dust that continues to mark the geometry of the system long after the original protoplanetary disk has dispersed. On a very clear night, far from city lights, this dust is visible to the unaided eye. It appears as a soft, slanting cone of pale light along the line of the ecliptic, rising from the horizon just after sunset or stretching upward just before sunrise. It is called the zodiacal light, after the constellations of the zodiac, which lie along the ecliptic. The zodiacal light is sunlight scattered by the dust of the plane back toward Earth. It is not a glow in the atmosphere. It is not an aurora. It is the disk of the solar system itself, made faintly luminous by the sun's light bouncing off the grains. To see it is to see, with the naked eye, the geometry of where we live. The zodiacal cloud is densest near the Sun and thinnest with distance outward. It also thins in the perpendicular direction, falling off quickly above and below the plane. There is a slightly brighter band, often called the asteroid belt dust band, that marks the contribution from collisions in the main belt between Mars and Jupiter. There is a much fainter outer contribution from the slow grinding of icy bodies far beyond Neptune. From the inside, the disk is a soft glow along one line of the sky. From above, it would appear as a wide, flat sheet of dust, the planets threading slowly through it like beads along their orbits, the inner regions brighter and the outer regions thinning into darkness. The geometry of dust is part of why the vertical axis of the solar system is so strange. Looking outward along the plane, the line of sight passes through more dust, more starlight scattered by that dust, more local light pollution from the solar system itself. Looking perpendicular to the plane, the line of sight passes through almost none of this. The sky directly above the Sun's north pole and directly below its south pole is among the cleanest possible views of the rest of the universe from anywhere inside our own system. The disk, which gives us our home, is also what crowds the rest of the sky. The directions perpendicular to it are the directions where the universe is least obscured. You might already have an intuition for the ecliptic without having heard the word. If you have ever watched Venus appear low in the west after sunset, and noted that Jupiter sat along the same imaginary curve, and that the moon followed that same curve a few nights later, you were tracing the ecliptic with your eyes. The planets do not wander across the sky in random directions. They keep to a single line, because they keep to a single plane, because they were all born in the same disk. The line they trace is the disk, seen edge-on from where we stand. Astronomers use two main coordinate systems to describe positions in the sky, and both of them are tied to the geometry of our local environment. One uses the celestial equator, Earth's equator, projected outward onto the sky as its reference plane. The other uses the ecliptic. The two planes are tilted with respect to each other by about 23.5 degrees, which is the same tilt that gives Earth its seasons. Earth's axis of rotation is not perpendicular to the plane of its orbit, and this tilt means that the celestial equator and the ecliptic cross each other in two places, called the equinoxes. For the purposes of tonight, the listener only needs to feel that there is one natural plane in the solar system, that the planets share it, and that up and down relative to that plane is a direction almost nothing in our experience ever moves. The disk of the solar system is itself nested inside a far larger disk, the disk of the Milky Way galaxy. The Milky Way is a slowly spinning spiral, hundreds of thousands of light years wide, made of several 100 billion stars and a great deal of gas, dust, and dark matter. Its disk, like the disk of the solar system, is a fossil of its rotation, flattened over the long ages of its formation. But the disk of the Milky Way is not the same disk as the disk of the planets. The two planes are tilted with respect to each other by roughly 60 degrees. The Sun and its planets orbit the galactic center in their own private plane, oriented quite differently from the plane of the galaxy as a whole. This difference is barely felt from inside the solar system, but it matters for the question of what the sky looks like from above the Sun. From Earth, the band of the Milky Way cuts horizontally across the night sky. The bright bulge of the galactic center, visible most clearly from southern latitudes during certain months of the year. From a vantage point above the Sun's north pole, that horizontal band would tilt sharply upward. The bright bulge of the galactic center would lie in a different direction relative to the ecliptic. The constellations of the southern sky, the dark dust lanes that thread through the band of stars, the soft glow of the central regions all would appear, from above, in a quite different geometric arrangement than they do from here. The stars themselves would be the same stars. The sky would be the same sky. But the orientation would be unfamiliar in a way that is hard to imagine until one stands somewhere unfamiliar enough to see it. The sun itself moves through the galaxy, drifting at roughly 200 kilometers per second, relative to the average motion of nearby stars. The direction of that motion, projected against the background stars, points toward a part of the sky in the constellation of Hercules. The sun has been carrying its planets along on this slow drift for the entire history of the solar system, sweeping through a tremendous volume of the galaxy as it goes. Around it, in a roughly elongated bubble carved by ancient supernova explosions, lies a region of low-density interstellar gas called the local bubble. The shape of that bubble is itself uneven, with one side opening more cleanly through to the rest of the galaxy and another side bounded more closely. The direction below the sun's south pole, in galactic terms, opens into one of the clearer of these sightlines. The plane of the planets, the plane of the galaxy, and the directions perpendicular to each of them all overlap and intersect across the same patch of sky we look out into every night. We live at the meeting point of multiple disks, multiple flatnesses, multiple long-settled rotations. The geometry of where we are is not arbitrary. It is the layered result of clouds collapsing, gravity organizing, rotation flattening, and time enforcing its preferences. The simplest single fact about the solar system, the fact that lets all of the rest of tonight's exploration make sense, is that it is flat. The disk is real. The vertical axis is real. And the rest of the evening is a long, quiet consideration of how seldom we have ever looked along that vertical axis and what we might see if we did. The most important fact about leaving Earth is one that is rarely stated plainly outside of mission planning rooms, and yet it determines almost everything about how spacecraft move through the solar system. We are not standing still. The ground beneath the listener is moving, not because of any earthquake or local motion, but because the entire planet is sweeping sideways around the sun at a speed that is difficult to feel because it is so steady and so constant. Earth's orbital speed is roughly 30 kilometers per second. Every second, the planet has carried itself 30 kilometers further along its orbit. Every minute, 1,800 kilometers. Every hour, more than 100,000. The listener, the room they are in, the building, the air, the oceans, the rocks, the molten interior, the whole planetary system, all move together at the same enormous sideways speed. A rocket, lifting off from Earth's surface, inherits all of this sideways motion the moment it leaves the ground. It does not need to acquire orbital velocity from scratch. It already has 30 kilometers per second of sideways motion around the sun by simply existing on a launch pad on Earth. What it must add to reach orbit around Earth is the additional speed required to circle Earth itself, which is about 8 kilometers per second relative to Earth's surface. What it must add beyond that to escape Earth and travel to the Moon or Mars or Jupiter is more modest still, because the sun's gravity is already in charge of the basic shape of those journeys. The rocket essentially nudges its inherited orbit into a new one. Nothing it does cancels the sideways motion around the sun that it was born with. Nothing it does ever returns it to a state of rest with respect to the sun. This single inheritance is why almost every spacecraft in the history of spaceflight has ended up moving more or less within the plane of the planets, and why almost nothing has ever moved above or below that plane in any meaningful way. To rise above the ecliptic, a spacecraft does not simply need to climb. It needs to erase the 30 kilometers per second sideways motion it was born with and replace it with an equivalent motion in a different direction, a direction that points up and out of the plane. The plane is not a road. It is a current. Everything in it is being carried along, and changing course is enormously more expensive than continuing along the flow. Mission planners use a term for the budget of change a spacecraft can perform with its onboard fuel. They call it delta V, the change in velocity the spacecraft can produce. Delta V is the currency of the solar system. Every maneuver costs some, and once a vehicle has spent its delta V budget, it can do no more. The size of the budget depends on how much fuel the vehicle started with and how efficient its engines are. Chemical rockets, the kind that lift things off Earth and have been refined over the last 70 years of practical engineering, have particular efficiencies that set practical ceilings on how much delta V a mission can carry. The numbers below are rough but accurate enough for tonight. Reaching low Earth orbit from the surface costs roughly 9 to 10 kilometers per second of delta V. Most of this is spent fighting gravity and atmospheric drag during the early climb and adding the sideways speed needed to stay in orbit once the rocket is above the atmosphere. Leaving Earth orbit for the Moon costs another 3 or 4 kilometers per second. A transfer to Mars, using the standard low-energy trajectory and a launch window when the planets are favorably aligned, costs roughly 4 kilometers per second of delta V beyond Earth orbit. A transfer to Jupiter, with or without gravity assists, costs roughly 6.5 kilometers per second beyond Earth orbit. These are the familiar destinations, and the budgets to reach them are entirely within the capability of modern rockets, provided the spacecraft is small enough and the mission is planned carefully. A trajectory that would actually leave the plane of the solar system, that would point up out of the ecliptic into the empty sky above or below, requires erasing most of Earth's sideways orbital motion and replacing it with an equivalent motion in the perpendicular direction. The cost is roughly 30 kilometers per second of delta V from low Earth orbit. This is more than any chemical rocket has ever delivered to a single spacecraft. The largest interplanetary missions ever flown have delivered total delta V budgets in the range of 15 to 20 kilometers per second over the full course of their lives, and most of that has been used to slow down, to enter orbit around a destination planet, or to adjust trajectory at the destination. The direct climb out of the plane is not slightly out of reach. It is wildly out of reach. Sit for a moment with the strangeness of these numbers. Sending a spacecraft all the way to Pluto, at the outer edge of the planetary system, costs less delta V than sending the same spacecraft directly upward, perpendicular to the plane, to a height no greater than Earth's own orbit. Reaching the icy bodies on the rim of the solar system is easier than reaching the empty sky immediately above the Sun. The ecliptic is not a road we are driving along. It is a current we are caught inside, one that has been carrying everything in the solar system along the same direction for billions of years. Stepping out of the current is, by orders of magnitude, harder than continuing within it. The reason for this counterintuitive ranking is geometry. To go outward, a spacecraft can simply add a little velocity along the direction it is already moving, and slowly widen its orbit into a long ellipse that reaches Jupiter or Saturn or Pluto. This is the gentle, fuel-efficient maneuver behind nearly every outer system mission ever flown. The Sun's gravity does most of the actual travel work. The spacecraft only needs to give itself a small extra push at the right moment, and the orbit takes care of the rest. To go upward, the spacecraft has to push perpendicular to its existing motion. None of the existing motion helps. None of the Sun's gravity helps in the climb itself, because the Sun's gravity points inward, not down. Every kilometer per second of vertical velocity has to be paid for in full, with fuel burned in space, with no shortcut available. This is the underlying reason the polar regions of the Sun are, in spaceflight terms, more remote than than the outer planets. They are not far away. The Sun's poles are roughly the same distance from Earth as the rest of the Sun. They are only difficult to reach because reaching them means escaping the plane that gravity locked everything into 4.5 billion years ago. The geometry of the solar system is welcoming to anything that wants to follow the existing flow, and inhospitable to anything that wants to swim across it. The Sun's poles are inhospitable in this sense. They sit in a region of space that the solar system itself does not visit. There is, however, one way around the delta V wall, and it is the trick on which almost every distant mission of the last 60 years has depended. A spacecraft on a carefully chosen path can fly past a planet and use that planet's gravity to redirect itself, gaining or losing speed relative to the Sun without burning any fuel. The planet, being unimaginably larger, loses or gains a microscopic amount of orbital speed in return. The energy is conserved. The spacecraft borrows a small fraction of the planet's orbital energy, and the planet loses an immeasurably tiny amount of its own. The maneuver is called a gravity assist, or a planetary flyby, or a swing-by, and it is the closest thing in physics to a free lunch. A single flyby can change a spacecraft's speed by several kilometers per second per encounter, depending on the planet's mass, the speed of the encounter, and the geometry of the approach. Heavier planets give larger boosts. Faster approaches give larger redirects. The angle at which the spacecraft skims past the planet determines whether the boost is added to the existing speed, subtracted from it, or redirected sideways. A skillful trajectory designer can use a sequence of carefully timed flybys to shape a spacecraft's path in ways that pure rocket fuel could never afford. Jupiter, the most massive planet, is the most powerful natural slingshot in the solar system. A close flyby of Jupiter can change a spacecraft's speed by 10 kilometers per second or more in a single pass. With the right approach geometry, Jupiter can throw a spacecraft entirely out of the plane of the planets, redirecting its motion sharply upward or downward relative to the ecliptic. The cost in delta V is essentially zero. The cost in mission design is enormous because the spacecraft must arrive at Jupiter at exactly the right time, with exactly the right approach angle, to achieve exactly the desired departure trajectory. The launch window for such a mission is narrow, and the trajectory once committed cannot be easily redrawn. Venus, smaller but conveniently close, can be used many times in sequence to slowly bend a trajectory upward. Each pass adds a small amount of inclination, which is the technical term for the tilt of an orbit relative to a reference plane. A spacecraft that loops between an inner orbit and Venus repeatedly can accumulate inclination one flyby at a time, climbing gradually out of the ecliptic over the course of many years. The process is slow, but it is patient, and patience costs nothing in delta V terms. The spacecraft pays in years of mission lifetime, rather than in tons of fuel. Gravity assists do not violate any law of physics. Energy is conserved. Momentum is conserved. The spacecraft borrows orbital energy from the planet, which loses an immeasurably tiny amount in exchange. Over many flybys, this is the difference between a mission that can reach the Sun's poles and one that cannot. Almost every long-range mission ever flown to the outer solar system has used at least one gravity assist along the way. The technique is, in a real sense, what makes solar system exploration possible at all. There is a classical problem in celestial mechanics that captures the difficulty of moving between 2 points in space. The problem asks, given a starting point, an ending point, and a fixed travel time, what orbit connects them? The mathematical answer has elegant solutions in the plane of the planets, where everything is moving in the same direction at compatible speeds. Out of plane, the problem becomes severe because the connecting orbit has to fight every familiar shortcut. There is no need to dwell on the mathematics. The point is only that the universe makes it easy to move between bodies that share a plane and hard to move between a body and a point in empty space that does not share that plane. The geometry rewards staying in the disk and penalizes leaving it. This is the deeper reason that mission designers, given a list of destinations to consider, almost always rank the polar regions of the Sun as far harder than the icy bodies at the edge of the system. The icy bodies are in the disk. The poles of the Sun are not. The disk is generous to travelers within it and frugal to travelers who try to leave it. Nothing in the universe forbids escape. It simply costs more than the available rockets can deliver in a single straight ascent. Every spacecraft that has ever climbed out of the plane has done so by using planets as ladders, exchanging time and complexity for the missing delta V. The history of solar system exploration is, in a sense, the history of working around this single problem. Spacecraft to the inner planets ride existing orbital flows and add small corrections. Spacecraft to the outer planets ride existing orbital flows and use gravity assists for the long stretches. Spacecraft that aim to leave the plane entirely must combine both techniques with patience added on top. Every familiar mission profile is shaped by the fact that the solar system is flat, and that flatness is enforced by the long sideways speed every spacecraft inherits at the moment of launch. The plane is not just a description of where the planets happen to be. It is a kind of structural constraint on what spaceflight can do, against which every mission must press. Even the language of mission design reflects this. Spacecraft are described by their delta V budgets, by their inclination capabilities, by their flyby sequences. The shape of a trajectory is named not for where it ends, but for how it bends, how it leans, how it converts time and gravity into the changes of direction it needs. A mission to reach a planet on the disk is described in simple terms. A mission to climb above the disk is described in nested ones, with several phases, several flybys, several years of patient orbit shaping. The two kinds of missions are not on the same kind of map. They live in different parts of the engineering imagination. And so the prison of orbital velocity is not exactly a prison. It is more like a current. The solar system flows in one direction, around its central star, in one wide, flat sheet of motion that has been turning for billions of years. To go anywhere in that sheet is straightforward. To leave it is not. The math is the same math that governs every orbit, the same conservation of angular momentum that flattened the original protoplanetary cloud, the same gentle laws repeated at every scale. There is no villain in this geometry. There is only the patient consequence of how a solar system, once formed, holds on to its shape. We live inside that consequence, and so does every spacecraft we have ever launched. Climbing out of it is not impossible. It simply requires a different kind of mission than the ones we have mostly been flying. Almost everything we have ever observed about the Sun has been observed from its equator. The sunspots in the photographs astronomers take from Earth, the flares that erupt and are recorded on ultraviolet film, the slow turning of magnetic features across the visible disk, the bright streamers of the corona seen during total solar eclipses, the long-term tracking of the 11-year cycle of activity. All of this is essentially equatorial science. The Sun's poles, the two regions where its axis of rotation meets its surface, are largely invisible from Earth and from any spacecraft that has stayed within the plane of the planets. Even at the most favorable geometry, the poles are foreshortened, seen at a shallow grazing angle, lost in projection across the curved face of the star. To see them properly, a vantage point above or below the Sun is required, and that vantage point has been available for only a small fraction of the history of solar physics. This matters more than it might initially sound, because the poles are not minor regions of the Sun. They are not edges, or remote outposts, or quiet zones that can be safely ignored. They are where some of the most distinctive solar behavior happens. They are where the fastest solar wind originates. They are where the global magnetic field reverses every 11 years. They are where the engine of long-term solar variability appears to live. Much of what the Sun does, viewed at the equator, is the visible consequence of processes that begin at the poles. To miss the poles is to study the symptoms while missing the source. The concept that opens this part is the coronal hole. A coronal hole is a region of the Sun's outer atmosphere, the corona, where the magnetic field lines do not loop back to the surface, but instead open out into space. From these regions, the corona's plasma, the hot ionized gas that fills the Sun's outer atmosphere, can flow outward, unimpeded, along the open field lines. Coronal holes appear, in ultraviolet images of the Sun, as dark patches, because the plasma in them is less dense than the plasma in the surrounding closed-loop regions. Dark, in coronal terms, simply means thinner. During the quiet phases of the 11-year solar cycle, persistent coronal holes occupy both polar regions of the Sun. They are large, stable, continuous structures, sometimes lasting for years without significant change. The polar coronal holes are where the famous fast solar wind originates. From the polar holes, the wind streams outward at roughly 700 to 800 kilometers per second. This is nearly twice the speed of the slower wind that comes from the equatorial regions. The fast wind is also chemically different from the slow wind, with subtly different ratios of elements and ionization states, reflecting the different conditions in which the two winds form. The slow solar wind, by comparison, drifts outward at roughly 300 to 500 kilometers per second. It originates from the boundaries of coronal holes and from a region near the equator called the streamer belt, where the Sun's magnetic field forms the bright looping structures visible during a total eclipse. The slow wind is more turbulent than the fast wind, more variable in density, less uniform in composition. The two kinds of wind exist together in the heliosphere, blowing past Earth and the other planets in alternating streams as the Sun rotates and presents different regions to face the planets in turn. Where the fast wind from the poles meets the slow wind from the equator, the Sun's magnetic field forms a thin, undulating boundary surface that spirals outward through the entire solar system. This surface separates regions of opposite magnetic polarity, north on one side, south on the other, and it twists with the Sun's rotation into a long, slowly turning spiral pattern. It is often described as a ballerina skirt, because as the Sun spins, the skirt's hem rises and falls relative to the equamis, sweeping past the planets in a slow, regular rhythm. The technical name for this surface is the heliospheric current sheet, and it is the largest single magnetic structure in the solar system. Earth crosses the heliospheric current sheet several times during each solar rotation. Each crossing produces small but measurable changes in the magnetic environment around the planet. These crossings, when they happen during periods of stronger solar activity, can contribute to small geomagnetic disturbances. The current sheet is not visible to the eye. It is mapped indirectly by spacecraft that pass through it and measure the local magnetic field, and by ground-based observations of the corona that infer the sheet's likely shape from the visible streamer patterns. The amplitude of the ripples in the current sheet rises and falls with the solar cycle. Near solar maximum, When the Sun is most active and its magnetic field is most disordered, the sheet is wildly tilted, with peaks and troughs that climb steeply away from the equator. Near solar minimum, when the Sun is quietest, the sheet flattens to nearly a flat plane along the solar equator. The sheet's geometry is one of the slow rhythms of the heliosphere, beating gently across the years. The shape of the heliospheric current sheet, viewed from above the Sun, would be one of the most striking sights in the solar system. A slowly spinning, slowly warping membrane of magnetic structure stretching outward past the planets, undulating with the Sun's seasons, reflecting the global state of the solar dynamo at every distance. No image of the current sheet has ever been made directly. Its shape is inferred from in situ measurements taken as spacecraft cross through it, and from coronal observations from inside the plane. A view from above would resolve, for the first time, what its true geometry actually is, and how it changes with the Sun's mood. Roughly every 11 years, the Sun's magnetic field reverses. What was the north magnetic pole becomes the south, and the south becomes the north. This is one half of a full 22-year magnetic cycle, sometimes called the Hale cycle, and it appears to drive much of the activity visible on the Sun's surface: the rise and fall of sunspot numbers, the strength and frequency of flares, the structure of the corona, the size and shape of the polar coronal holes. The reversal does not happen all at once. It is a gradual process that unfolds across the years of the cycle. The reversal originates in the polar regions. Throughout each cycle, magnetic flux of the new opposite polarity migrates from active regions at lower latitudes toward the poles. Sunspots and active regions tend to come in pairs with opposite polarities, and one polarity systematically leads the other across the face of the Sun. The trailing polarity, by various processes of diffusion and slow flow, migrates poleward over the years. When enough flux of the opposite polarity has accumulated near a pole, it cancels the existing polar field, and the global polarity flips. The two poles do not always reverse at exactly the same time. One pole sometimes leads the other by months or even years. During these intervals, the Sun briefly has a global magnetic structure that is more like a quadrupole than a dipole, with multiple magnetic poles at unusual latitudes. The asymmetry resolves itself as the second pole eventually catches up, and the Sun settles back into a clean dipole with the reversed orientation. The whole process, from the buildup of new flux to the final settling of the reversed field, takes most of the 11-year cycle to complete. The strength of the polar magnetic field at the end of one cycle appears to predict the intensity of the next cycle. A strong polar field generally precedes a strong sunspot cycle 11 years later. A weak polar field precedes a weak cycle. The connection is not a hard rule, and the precise mechanism is still being worked out, but the correlation is strong enough that astronomers use polar field measurements as one of the more reliable forecasts of upcoming solar activity. This makes the poles, in a real sense, the dynamo room of the Sun. The activity visible on the equator is the result. The cause lives at the latitudes we cannot easily see. The few existing images of the polar regions, taken at limited resolution from the partial vantage points achieved so far, suggest that the surface structure near the poles is different from the structure near the equator. There are no large sunspots at the poles. Instead, the magnetic field appears to break up into countless small flux concentrations, woven into a fine, tangled network. The visible solar surface near the poles has a different texture than the equatorial surface, smaller, less organized magnetic features, rather than the broad active regions and sunspot groups that dominate the latitudes where most of the Sun's familiar drama plays out. Long, thin streams of plasma, called polar plumes, extend outward from the polar regions, like grass blades, aligned with the open magnetic field lines. The plumes are best seen during total solar eclipses, when the bright disk of the sun is briefly hidden and the fainter corona becomes visible. From inside the plane, the plumes appear as faint rays curving away from the sun's polar limbs. From directly above a pole, they would appear as a radiating pattern, spreading outward in every direction along the open field lines. Each plume a thin column of slightly denser plasma, threading through the surrounding fast wind. You can imagine the sun seen not as a disk, but as a sphere viewed from above its axis of rotation. The familiar dark spots of equatorial activity would be replaced by a quiet, granular surface, threaded through with delicate plumes radiating outward like the petals of a slowly spinning flower. The brilliant, fast wind would stream away in long, straight rays. The geometry would feel less like a star and more like the open eye of something patient and very old. The magnetic field laid bare in a pattern no equatorial view can quite reveal. The poles also matter for the long-term magnetic memory of the sun. The reversal cycle does not always proceed at the same intensity. Some cycles are stronger than others. There are even centuries-long periods when the sun's activity drops noticeably, with weak sunspot cycles and quieter magnetic behavior. These extended minima of solar activity appear to be connected to weaknesses in the polar field, sustained over many cycles. The sun's variability on timescales of decades and centuries seems to originate, like the cycle itself, in the slow accumulation and decay of magnetic flux at the poles. Even the geometry of solar magnetic eruptions reflects the influence of polar structure. The large filaments and prominences that occasionally lift off from the sun's surface tend to align with the boundaries between regions of opposite polarity. As the magnetic field migrates poleward through the cycle, these boundaries move with it, and the locations of major eruptions shift latitudinally across the years. The pattern, charted over many cycles, traces out the famous butterfly diagram of solar activity, with sunspot bands appearing first at high latitudes early in each cycle and migrating toward the equator as the cycle matures. All of this is the visible consequence of processes that begin at and return to the poles. The poles are where the field accumulates, where it reverses, where the fast wind originates, where the long memory of the sun's behavior is stored. They are the most active site of the most fundamental processes of solar physics. And they are the regions about which we know the least, because they are the regions we have most rarely visited. The polar coronal holes themselves are remarkable structures in their own right, and they merit a few more unhurried sentences. A polar coronal hole, during the quietest phases of the solar cycle, can cover an enormous fraction of the sun's upper or lower hemisphere. Seen in ultraviolet light, the dark region of the hole extends from the pole itself down to perhaps 60 degrees of latitude, sometimes further. The hole's boundaries are not straight or smooth. They wander irregularly across the high latitudes, with bays and peninsulas of open magnetic field intruding into the surrounding closed-loop corona. The shapes shift over weeks and months, but the overall existence of a large polar hole during solar minimum is one of the most persistent features of the sun's behavior. As the solar cycle advances toward maximum, the polar coronal holes shrink. The migration of opposite polarity flux toward the poles, the increasing complexity of the magnetic field at lower latitudes, the eventual cancellation and reversal of the polar field, all of these processes break up the polar holes during the active phase of the cycle. At solar maximum, the polar holes can be almost absent, with small, isolated coronal holes appearing at various latitudes instead. After the field reversal completes, the polar holes gradually rebuild themselves with the opposite magnetic polarity, growing back to their full size as the cycle approaches the next minimum. The fast solar wind that streams from the polar holes carries with it a particular signature in the heavy elements it contains. The ratio of certain elements in the fast wind compared to the slow wind differs in ways that reflect the different conditions at the origin of each. The slow wind, originating in the closed-loop corona at lower latitudes, has a composition that has been processed through prolonged residence in the corona, with certain elements preferentially enhanced. The fast wind, escaping more directly through the open field lines of the polar holes, carries a composition that more closely resembles the underlying solar photosphere. These compositional differences are subtle but measurable, and they help astronomers trace any given parcel of solar wind back to its likely origin on the Sun's surface. The microscopic structure of the polar surface, where it can be resolved at all, shows the familiar granulation pattern that covers the rest of the Sun. The granulation is the visible signature of convection cells in the outer layers of the Sun, with hot plasma rising in the bright centers of each cell and cooler plasma sinking along the darker edges. Above the granulation, near the poles, the magnetic field threads upward in countless small bundles. Each bundle marks where a flux concentration has worked its way out of the convective layer and into the corona above. The bundles arrange themselves into the larger plume structures that radiate outward, and the plumes together form the visible texture of the polar corona as seen during eclipses or from high-inclination spacecraft. The polar regions also play a quieter role in the Sun's rotation. The Sun does not rotate as a solid body. Its equator rotates faster than its poles, completing one rotation in about 25 days at the equator and more than 30 days at high latitudes. This pattern is called differential rotation, and it is one of the engines that helps wind up the Sun's magnetic field over the course of each cycle. The contrast between fast equatorial rotation and slower polar rotation stretches the magnetic field lines around the Sun, building up the twisted, complicated structures that eventually produce sunspots, flares, and the eventual reversal of the polar field. The poles, in this sense, set one end of the differential rotation pattern that drives the whole cycle. Beneath the visible surface, the deep interior of the Sun also rotates differentially, with patterns that can be probed by techniques that listen to the Sun's own internal oscillations. The interior rotation patterns vary with both latitude and depth, and the boundaries between regions of different rotation rates are thought to be where the strongest magnetic field generation happens. The poles play their role in this deep interior architecture as well, though the details are still being worked out. The overall picture is that the magnetic activity of the Sun is shaped by a long chain of processes that begin in the deep interior, propagate through the convective layers, emerge at the surface as sunspots and active regions, migrate poleward across the years, and eventually accumulate at the poles to produce the reversal that sets up the next cycle. The poles are the end station of this long chain, and the place where the cycle's memory is stored from one phase to the next. The reason for this gap is the geometry from Part 2. The poles cannot be seen well from inside the plane of the planets. To see them properly requires a spacecraft above or below the plane, and such spacecraft have been rare. The poles are not far. They are just unreachable by the kinds of missions that have dominated the history of spaceflight. The Sun has been spinning, reversing, flaring, and streaming its polar wind for billions of years, with no one watching from the directions where the most important geometry happens. The two missions that have ever tried, in their different ways, to fill that gap are the subject of the next part. Only 2 spacecraft in the history of spaceflight have ever climbed meaningfully out of the ecliptic to observe the Sun's poles directly. Both stories are remarkable, and both are partial. The first reached high solar latitudes, but carried no camera that could photograph the sun's surface directly. The second is currently underway, gradually tilting its orbit by repeated flybys of an inner planet, and has very recently delivered the first close direct images of one of the sun's poles ever obtained by any spacecraft. Together, they represent the entirety of human experience above the plane of the planets. Neither has been able to hover. Both have been moving past, sampling briefly, then sweeping back through whatever portion of the disk their orbits next carry them through. The first mission to climb above the ecliptic was a joint effort between a North American space agency and a European one, planned over the course of many years and launched out of low Earth orbit aboard a winged orbital vehicle. The spacecraft was small for an interplanetary probe, with a single large dish for communication and a spinning body to keep its instruments distributed evenly around the sun. It carried instruments for measuring magnetic fields, solar wind particles, energetic ions, dust, radio waves, and the populations of cosmic rays at high latitudes. What it did not carry was a high-resolution telescope. There were no cameras on board that could photograph the sun's surface or its detailed coronal structure. The mission's contribution was to measure the environment at high latitudes, not to image it. The trajectory the first mission flew was one of the most elegant pieces of trajectory design ever attempted. The spacecraft launched outward from Earth, not toward the sun, but away from it, on a long, looping path toward Jupiter. It used Jupiter's enormous gravity in a carefully timed flyby to redirect its trajectory sharply out of the plane of the planets. After the encounter, its orbit was tilted by roughly 80 degrees relative to the ecliptic, almost perpendicular to the plane of everything else. The spacecraft then began looping around the sun on this tilted orbit, climbing high above the ecliptic at one extreme of its loop and diving deep below it at the other. The maneuver was extraordinary because it could not have been done with chemical fuel alone. The delta V required to tilt an orbit by 80 degrees from low Earth orbit by direct ascent would have been many tens of kilometers per second, far beyond what any chemical rocket has ever delivered. By taking the long detour out to Jupiter first, the spacecraft was able to use Jupiter's gravity to provide essentially all of the inclination change for free. The trajectory took years longer than a direct climb would have, but it accomplished what no direct climb could have done at all. It was the first practical demonstration that the sun's polar regions, while expensive to reach in delta V terms, could be reached at all if the mission was clever enough with its use of planetary gravity. The scientific harvest from the first mission was substantial. It confirmed, for the first time by direct in situ measurement, that the fast solar wind streams predominantly from the polar regions, and that the slow wind comes from low latitudes. Before this mission, the polar versus equatorial origin of the two wind regimes had been inferred from ground-based observations and modeled with theoretical work, but no spacecraft had ever flown above the plane to verify the picture directly. The first mission flew through both polar regions and measured the wind speeds, compositions, and magnetic structures it encountered. The fast wind was there, exactly where the models had predicted it would be. The mission also confirmed that the heliospheric current sheet does indeed surround the sun in the way the ballerina skirt picture had described. As the spacecraft climbed to higher latitudes, the crossings of the current sheet became less frequent, exactly as expected if the sheet were a roughly equatorial structure that warped only modestly into higher latitudes. The geometry of the current sheet, as a function of solar latitude and solar cycle phase, was mapped for the first time from a vantage point that could actually see how it changed with elevation above the plane. A more unexpected discovery from the first mission concerned the large-scale structure of the sun's magnetic field at distance. Within the immediate polar regions, the field was as polar as the surface measurements had suggested it should be, with clear, open field lines stretching outward from the polar coronal holes. But at greater distances from the Sun, the field was found to be surprisingly uniform with latitude. Once the spacecraft was well outside the immediate polar region, the radial component of the magnetic field became roughly the same in every direction, smoothed by the way solar wind plasma carries magnetic field with it across the heliosphere. The structure of the field, in other words, was more local than expected near the surface and more global than expected at distance. The first mission also sampled regions where no spacecraft had been before. High above the Sun, well out of the plane of the planets, the populations of cosmic rays, of interstellar dust grains drifting in from outside the solar system, and of energetic particles produced by solar activity were measured for the first time in environments that simply had not been observed in person. The cosmic ray fluxes at high heliospheric latitudes told astronomers something about how galactic cosmic rays penetrate the heliosphere from above, a question that could not be addressed from inside the plane, where the geometry was different. The mission operated for nearly 2 decades before its instruments fell silent and its mission was formally ended. The orbit it left behind continues to loop above and below the Sun, empty now, the spacecraft inert, the dish that once communicated with Earth no longer transmitting. The orbit itself is one of the more remarkable artifacts of spaceflight, a perpetual high-inclination loop around the Sun, with the silent spacecraft carried along it for as long as the orbit lasts. There is no rescue planned. There is no successor flying the same orbit. What the first mission could not do, despite all of its scientific accomplishments, was take a picture. It could measure the wind, but it could not photograph the surface from above. It could measure the magnetic field at the poles, but it could not image the magnetic structures themselves. The visual landscape of the polar regions of the Sun, the actual appearance of the polar surface, and the polar corona remained almost entirely unknown after the first mission ended. The closest thing to a polar image that existed before recently was a foreshortened view from the ecliptic, with the pole tilted toward the observer at a shallow angle and most of the detail lost in projection across the curved limb. Decades later, a European-led mission launched with a different strategy. Instead of using Jupiter to bend its trajectory sharply once and for all, the new spacecraft uses repeated flybys of Venus to bend its orbit gradually, one small inclination change at a time. With each pass of Venus, the spacecraft's orbit becomes a little more inclined to the ecliptic. The process is patient. Each flyby adds only a few degrees of tilt. But over the course of many years and many flybys, the spacecraft climbs steadily out of the plane, reaching higher and higher solar latitudes with each successive loop. The new spacecraft carries a full suite of imaging instruments, in a deliberate complement to what the first mission lacked. There is a high-resolution telescope for imaging the solar surface at visible wavelengths. There is a magnetograph for measuring the surface magnetic fields directly, latitude by latitude. There are ultraviolet images for capturing the structure of the corona and the chromosphere at the wavelengths where coronal plasma glows brightly. There are coronagraphs for imaging the corona by blocking out the Sun's bright disk. There are instruments for measuring the local solar wind and magnetic environment, complementing the imaging with in situ data. The mission is, in effect, a flying solar observatory designed to give the polar regions the same kind of treatment that equatorial regions have received for decades. The orbit of the new spacecraft takes it relatively close to the Sun at perihelion, the closest point of its orbit. Close enough that thermal management is a major design constraint. A specialized heat shield protects the instruments from the intense sunlight at perihelion. The heat shield has small doors that can open briefly when the spacecraft is far enough from the sun for the optics to look out safely. The shield itself is engineered with a specific surface treatment to reflect away as much sunlight as possible, keeping the rest of the spacecraft cool enough to function. The thermal challenges are significant, but they are solvable, and the design has been demonstrated to work across multiple close approaches. As of recently, the new spacecraft has begun reaching the orbital inclinations needed to image the polar regions. The first direct close images of one of the Sun's poles have now been returned. Earlier views from spacecraft within the ecliptic were limited by the foreshortening problem. The new images, taken from above the plane, show the polar surface and the polar corona at an angle that allows real structure to be resolved for the first time. The mission is expected to climb to even higher inclinations in the coming years, eventually viewing both poles in full. The first frames of the south polar region of the Sun, when they arrived, did not look like the equator. The surface texture was finer and more chaotic. The magnetic field was a tangle rather than a pattern, with countless small flux concentrations rather than the broad active regions that dominate equatorial latitudes. The polar plumes were resolved as individual rays of plasma extending outward from the polar coronal hole, leaning gently with the curvature of the rotating magnetic field. It was the first time human eyes had ever seen the Sun from this direction at any meaningful resolution. There is no archive footage of the Sun's poles from before this. There simply is none. The two missions together have established what could not be known from inside the plane alone. The first mission proved that the polar regions behave differently from the equator: different wind, different field, different particle environment. The current mission is filling in what the first mission could not: provide direct imagery, magnetic maps, ultraviolet structure of the polar corona, the visual appearance of the polar surface itself. Between them, they have demonstrated that a vantage point above the ecliptic is not a luxury for solar physics. It is required if the Sun is to be understood as a three-dimensional object, rather than as the flat disk that appears in every equatorial photograph. Even both missions combined have observed only a small fraction of what a true polar observatory could measure. Neither has been able to hover above a pole, holding station while the Sun rotated beneath it. Both have been moving past, on their own inclined orbits, sampling the polar regions during the brief intervals when their trajectories carried them high enough, then sweeping back toward lower latitudes as the orbits continued their loops. A spacecraft that could sit above a pole for years at a time, observing continuously, has not yet been built. The full polar story of the Sun, the one that would require sustained observation from a true polar vantage point, is still waiting to be written. The progress so far is enormous compared to the long history of having no polar observations at all. The remaining gap is also enormous compared to what a sustained polar mission could provide. Both things are true at once. The two missions are an opening into a vantage that had been closed for the entire history of solar physics. They are also a small first step into a region that remains, by any reasonable measure, almost entirely unexplored. The Sun's poles have been visited briefly. They have not yet been lived with. The instruments aboard each of these two missions deserve a closer look, because the instrument suite is what determines what kind of science any mission can do. The first mission's instruments were chosen to characterize the polar environment in terms of its physical conditions, the magnetic field strength and direction at high latitudes, the density and velocity of the solar wind particles, the composition of the energetic ions present, the populations of cosmic rays, the radio emissions produced by various plasma processes, the dust grains drifting through interplanetary space. Each of these measurements required a different instrument, tuned to detect a particular type of particle or wave or field. The spacecraft was, in a sense, a portable physics laboratory, designed to do measurements in regions where no laboratory had ever been before. The magnetic field instrument on the first mission used what is called a flux gate magnetometer, a kind of sensor that measures the strength and direction of a magnetic field with high precision. The magnetometer was mounted on a long boom extending out from the main body of the spacecraft to keep it as far as possible from any magnetic interference from the spacecraft's own electronics. The boom was deployed shortly after launch and remained extended throughout the mission, with the magnetometer at its tip, taking continuous measurements of the local magnetic field as the spacecraft moved through different regions of the heliosphere. The resulting record is one of the most detailed continuous magnetic measurements ever made over such a wide range of solar latitudes. The particle instruments on the first mission included detectors tuned to different energy ranges, from the relatively cool plasma of the solar wind itself through the more energetic ions accelerated by solar flares and shock fronts, up to the very high energies of galactic cosmic rays arriving from outside the heliosphere. Each detector counted particles, measured their energies, and in some cases, identified their chemical species. The combined dataset provided the first comprehensive picture of the particle environment at high heliospheric latitudes, across a full range of energies and across more than a full solar cycle of time. The dust instrument on the first mission was a piezoelectric detector capable of registering the impacts of individual dust grains striking the spacecraft. Each impact produced a small electrical signal whose amplitude was related to the mass of the grain. By counting impacts and analyzing their characteristics, the instrument built up a picture of the dust environment in interplanetary space at latitudes far from the ecliptic plane, where the dust population had never been directly measured before. The results included evidence of interstellar dust grains drifting into the solar system from outside, distinguishable from the local solar system dust by their motion and characteristics. The radio and plasma wave instrument on the first mission detected the low-frequency electromagnetic waves and plasma oscillations that fill the heliosphere. These signals carry information about everything from the propagation of solar flare disturbances to the long-distance interactions between the solar wind and the heliospheric boundary far beyond the orbits of the planets. The instrument detected, for example, the radio signatures of shock fronts propagating outward through the heliosphere, and even, on occasion, signals associated with the boundary region where the solar wind meets the interstellar medium. The current mission's instrument suite was designed with a different philosophy. It includes the in-situ instruments that the first mission carried, but it also adds the imaging instruments that the first mission lacked. The Visible Light Telescope on the current mission can resolve features on the Sun's surface at scales of a few hundred kilometers, comparable to the finest details visible from ground-based telescopes during the rare moments of perfect atmospheric conditions. The magnetograph maps the surface magnetic field directly, producing pictures in which the strength and direction of the field at each point on the visible surface can be read at a glance. The ultraviolet images capture the corona at the wavelengths where its hot plasma emits most strongly, revealing the structure of the magnetic loops, the locations of active regions, and the boundaries of coronal holes. The coronagraphs on the current mission use a small occulting disk to block out the bright photosphere, allowing the faint corona to be imaged in white light. This is the same technique that produces the dramatic images of the corona seen during total solar eclipses, but it allows the corona to be observed continuously rather than only during the brief moments when an eclipse happens to be visible. The combination of the magnetograph, the ultraviolet images, and the coronagraphs gives the mission a layered picture of the Sun, from the visible surface up through the chromosphere and into the corona, all observed simultaneously from a single spacecraft. When the current mission's orbit has tilted enough for the polar regions to come into view, all of these instruments turn their attention to the new vantage. The polar surface, the polar magnetic field, the polar corona, the local plasma environment around the spacecraft, all are measured in the same coordinated way that the equatorial regions have been measured for decades from spacecraft within the plane. The result is the beginning of a polar science archive, comparable, in kind if not yet in volume, to the equatorial archive that has accumulated across a century of solar observation. Even with both missions combined, the volume of polar observations remains a small fraction of the equatorial archive. The first mission operated for nearly 2 decades, but its instruments were limited to in situ measurements, and its orbit carried it through the polar regions for only a fraction of each loop. The current mission is younger and has only recently reached the latitudes needed for polar imaging. Its archive of polar imagery is small but growing. The full picture of the Sun as a 3-dimensional object will continue to be assembled, frame by frame, measurement by measurement, across the years of the current mission and any future missions that follow it. The work is patient, the data is sparse, and the picture is still very much incomplete. The Sun's reach does not end at the orbits of the planets. The solar wind continues outward, thinning gradually as it goes, carrying the Sun's magnetic field with it across distances vastly greater than the planetary system itself. Eventually, the outward flowing wind slams into the surrounding gas and dust of the local interstellar medium, where the pressures of the wind and the pressures of the interstellar gas balance and a boundary forms. The region enclosed by that boundary, the great bubble of solar plasma carved out by the Sun's wind, is called the heliosphere. The boundary itself is the heliopause. Everything we know as our solar system, the planets, the asteroid belt, the Kuiper belt, the great inner reaches of the comet cloud, all live deep inside this bubble. The heliosphere is our local weather system, our local magnetic environment, our shield against the harsher conditions of interstellar space. The shape of the heliosphere, however, is one of the open questions of contemporary astronomy. And, like so much else in tonight's exploration, the difficulty in answering the question comes back to the fact that everything we have measured of the heliosphere has been measured from within the plane of the planets, from inside the disk that the entire solar system shares. The bubble that contains us has never been observed from outside, has never been imaged in plan view, has never been mapped from a vantage point that does not itself sit within the geometry the bubble defines. For decades, the standard mental image of the heliosphere was the shape of a comet. The Sun moves through the surrounding interstellar medium at a meaningful speed, roughly 26 kilometers per second, relative to the local gas, and this motion was thought to compress the heliosphere into a rounded nose on the upwind side, where the moving Sun pushes against the gas it is sweeping into, and to stretch the bubble into a long, tapering tail on the downwind side. The picture was the familiar one of a comet moving through its own atmosphere, with a bright head and a long flowing tail trailing behind. The comet-shaped picture was inferred from the way the solar wind ought to interact with the interstellar gas it pushes against, and from observations of similar bubble-like structures around other moving stars elsewhere in the galaxy. The model fit a great deal of the available data. It made specific predictions about the location of the upwind boundary, the structure of the magnetic field in the boundary region, and the geometry of the long downwind tail. For most of the late 20th century and into the early 21st, the comet model was the working picture of what our local bubble looked like. 2 distant spacecraft, launched generations ago and still traveling outward, have crossed the boundary of the heliosphere and entered interstellar space. Their measurements are the closest thing we have to direct observations of the boundary itself. Both spacecraft, however, crossed the boundary near the upwind nose of the heliosphere and roughly within the plane of the planets. They could not observe the tail. They could not observe the structure from above or below. They could only sample the small portion of the bubble that lay along their own trajectories, and what they measured was richer and stranger than the comet-shaped models had predicted. A more recent model, developed by astronomers studying the way the heliosphere interacts with the surrounding interstellar magnetic field, has proposed a very different shape. Rather than a long tail, the heliosphere in this model looks more like a deflated croissant, two lobes curving back from the nose, with a narrow waist between them and no extended tail at all. In this picture, the Sun's magnetic field, threaded through the solar wind, is strong enough at the boundary to pinch the bubble closed on the downwind side, preventing the long-tail geometry the comet model had predicted. The bubble in the croissant picture is more compact than the comet picture suggested, and its shape is more like a curved shell than a flowing teardrop. The croissant model fits some of the measurements taken inside the heliosphere, including the patterns of energetic neutral atoms particles that travel inward from the boundary and can be mapped without flying out to the boundary itself. It also predicts that the boundary on the downwind side would be much closer to the Sun than the comet model implied, perhaps not very much farther than the upwind boundary. The model remains debated. The data is sparse. The geometry is hard to reconstruct from in-plane measurements alone. The truth may lie somewhere between the two pictures, or in a configuration neither has imagined. There is something quietly humbling in the fact that no instrument, no telescope, no spacecraft has ever seen the heliosphere from outside its plane. Our solar system has been mapped, planet by planet, for centuries. Its outline, the soft boundary that separates the Sun's reach from the rest of the galaxy, has never been drawn. We are still waiting on the first portrait of our own home, the first image of the bubble we live inside, the first view of where the Sun's wind ends and the interstellar wind begins. To address some of these questions from within the heliosphere, without waiting for a spacecraft that can travel out of the plane, a planned interstellar mapping probe is being prepared. The new probe is designed to orbit relatively close to Earth and measure energetic neutral atoms streaming inward from the heliospheric boundary across the full sky. By recording the directions and energies of these inward streaming particles, the probe can infer the three-dimensional shape of the boundary without ever having to travel out to it. The mission will refine our understanding of the bubble from the inside, even as we continue to lack a true outside vantage point. Energetic neutral atoms are produced when charged solar wind particles streaming outward from the Sun interact with neutral atoms drifting inward from the local interstellar medium. The interaction strips an electron from one and gives it to the other, producing a fast, neutral particle that is no longer bound by the magnetic field and can travel in a straight line back through the heliosphere. Some of these neutrals are aimed back toward the inner solar system, where they can be detected by an appropriately designed instrument. The arriving neutrals carry information about where the interaction happened, and so they carry information about the structure of the boundary itself. By measuring the direction and energy of arriving neutrals across the full sky, the probe builds a kind of map of the heliospheric boundary. The technique is something like the way a medical imaging machine builds an image of internal structures from particles arriving from many angles. The geometry of the boundary is reconstructed from the patterns of inward traveling neutrals, even though no instrument has actually visited the boundary in person. The same technique has been used at lower sensitivity by a previous in-plane mission, which produced the first all-sky neutral atom maps of the heliospheric boundary, and which revealed an unexpected feature: a bright ribbon of enhanced neutral emission stretching across the sky in a particular geometric pattern. The ribbon's origin is still being worked out, but its existence demonstrated that the boundary region has more structure than the simplest models had suggested. The new probe will refine the resolution significantly, providing much sharper maps of the heliospheric boundary and improving the chances of discriminating between the comet shape and croissant shape models. The neutral atom approach is powerful, but it is indirect. It maps the bubble's boundary by inference rather than by sight. A spacecraft above the ecliptic could measure the boundary directly, observe the structure of the magnetic field at high latitudes, and, given enough time and fuel, possibly escape the heliosphere in a direction perpendicular to the disk, providing the first ever above or below crossing into interstellar space. No such mission is currently funded. The architecture exists on paper. The vehicle does not. The heliosphere is not a static object. It breathes with the solar cycle. As the sun's activity rises and falls over the 11-year cycle, the pressure of the solar wind changes, and the bubble responds. During solar maximum, when the wind is more intense, the bubble pushes outward and the boundary moves further from the sun. During solar minimum, when the wind is gentler, the bubble retreats inward and the boundary draws closer. The two spacecraft that have crossed the boundary did so at different phases of the cycle, and the boundary distances they measured reflected the cycle's state at the times of crossing. The interstellar medium that surrounds our bubble is not uniform either. The Sun is currently passing through a small, relatively low-density region of interstellar gas called the local interstellar cloud, which is itself embedded within a larger and even lower-density region called the local bubble. The local bubble is thought to have been carved by ancient supernova explosions tens of millions of years ago, which swept up the surrounding gas and dust and created the relatively empty cavity through which the Sun is now drifting. The boundary of our heliosphere therefore lies inside a bubble, within a bubble, the inner one made by the Sun's wind and the outer one made by the long-ago supernovae of nearby massive stars. When the Sun eventually drifts out of the local interstellar cloud and into a different region of the local interstellar medium, the conditions at the boundary of the heliosphere will change. A denser interstellar environment would compress the bubble. A lower density environment would let it expand. The boundary is not a wall. It is a balance, and the balance shifts as the surrounding pressures shift. The bubble we live in now is the bubble appropriate for the current external conditions, and it has been roughly the size it is today for most of recent solar history, give or take the slow fluctuations of the cycle. The geometry of the heliosphere also depends on the orientation of the interstellar magnetic field. The field, threading the local interstellar gas, exerts a measurable pressure on the boundary, and the direction of that pressure shapes the boundary in ways that simple models, without magnetic fields, cannot capture. The croissant model relies in part on the way the interstellar magnetic field interacts with the Sun's own field at the boundary, and the comet model assumes a simpler geometry in which the field plays a less dramatic role. Disentangling the field's contribution from the gas pressure's contribution requires measurements that can only be made at or near the boundary, and the existing measurements come from only two crossings, both in the same general direction. Beyond the heliopause lies the local interstellar medium proper. The space between stars is not entirely empty. It contains gas, mostly hydrogen, at very low densities, dust grains, magnetic fields, and a population of energetic particles called cosmic rays that fill the galaxy at large. The two spacecraft that have crossed the boundary are now sampling this interstellar environment directly, providing the first in situ measurements ever made of the conditions outside our local bubble. The measurements are still arriving, decades after launch, transmitted at low data rates across distances that grow with each passing day. Even further out, beyond the immediate interstellar neighborhood, the solar system is moving through the galaxy in a long, slow drift that has carried it through many different environments across its history. Over hundreds of millions of years, the Sun has passed through dense clouds, through quiet regions, through the spiral arms of the galaxy, and through the relatively empty inter-arm spaces. Each of these passages has been accompanied by changes in the heliosphere, with denser environments compressing the bubble and emptier ones letting it expand. The heliosphere we know today is the most recent in a long history of heliospheres, each shaped by the local conditions of its time. You can sit, for a moment, with the picture of where we are. A planet, orbiting a star, inside a bubble of solar wind, inside a region of interstellar gas, inside a larger cavity carved by ancient supernovae, inside a galactic spiral arm, inside the disk of the Milky Way, inside the small group of galaxies of which the Milky Way is the largest member, inside the much larger volume of the local universe. Each layer wraps the next. Each has its own shape and its own physics and its own quiet history. Tonight's question, the question of what sits above and below the Sun, is in part a question about how clearly we can see those nested layers from where we are. From inside the plane, we see them through the disk that contains us. From above the plane, we would see them through far less. The portrait of our home is incomplete, not because the universe is far away, but because we have only ever looked at it from one direction. The vantage point above and below the Sun, the vantage point from which the bubble could be seen in full, has been available in principle since the first protoplanetary cloud collapsed. It has been available to instruments only in the briefest and most partial of ways. The full picture is waiting. It has been waiting for a long time. It can continue to wait. The waiting is part of what the next part of tonight is about, what it would take to finally look from the directions we have not yet looked from, and how clever the spaceflight has to be to make that looking possible. There is a way to escape the plane of the planets that does not require 30 kilometers per second of brute force delta V from low Earth orbit. The trick is, of all things, to fall closer to the Sun first, and only then to push. It is one of the most beautiful principles in spaceflight, and it has been understood, in principle, since the earliest days of rocket science. The principle is counterintuitive only on first encounter. Once you have heard it explained, it has the quiet inevitability of a piece of geometry that could not have been otherwise. A spacecraft burning its engine deep in a gravitational well, close to a massive body, extracts more energy from the same burn than it would in empty space. The reason is that the spacecraft is already moving very fast at the bottom of the well, and the kinetic energy gained by a burn scales as the square of the velocity. Adding a small change in velocity to an object already moving very quickly produces a much larger change in energy than the same velocity change applied to an object moving slowly. The fuel does the same chemical work in either case, but the energy harvest is different because the spacecraft's existing speed amplifies what the fuel can accomplish. In intuitive terms, a kilogram of propellant burned at 100 kilometers per second changes the spacecraft's energy budget far more than the same kilogram burned at 10 kilometers per second. The kilogram of fuel is identical. The thrust the engine produces is identical. What is different is the velocity at which the burn happens, and that velocity multiplies the effect of the burn through the squaring relationship that governs kinetic energy. The principle is sometimes called the deep well burn or the perihelion maneuver, and it was formalized in the early decades of rocket science by a foundational figure in astronautics whose work laid much of the groundwork for orbital mechanics. The same principle is at work in every interplanetary mission ever flown. When a spacecraft arrives at a planet and wants to enter orbit around it, the engine burn is performed at the closest point of the approach, called periapsis, because that is where the spacecraft is moving fastest and where the burn does the most useful work. When a spacecraft wants to depart from a planet on a long outward trajectory, the engine burn is again performed at the closest point of the current orbit for the same reason. The deep well principle is the standard wisdom of how to spend fuel efficiently around any gravitating body. The reason it matters for tonight's exploration is that the Sun is the deepest gravitational well in the solar system, and a burn near the Sun extracts more energy than a burn anywhere else. Apply the principle to the Sun, and the result is one of the most extreme and most elegant maneuvers in proposed spaceflight. A spacecraft, launched from Earth, falls inward toward the Sun. The Sun's gravity accelerates it to enormous speed as it descends, well over 100 kilometers per second at the closest approach. At that perihelion, deep in the Sun's gravitational well, the spacecraft fires its engine briefly and intensely. Because of the deep well principle, the small amount of fuel burned at that velocity produces a vastly greater change in the spacecraft's orbital energy than the same burn at Earth's distance would have produced. After the burn, the spacecraft swings back outward, but now on a wildly different orbit. With the right burn direction, that new orbit can carry it out of the plane of the planets entirely, on a trajectory that would otherwise have been impossibly expensive. The maneuver is breathtaking on paper. A modest amount of fuel, burned at the right moment, can deliver a spacecraft to a polar orbit around the Sun for a small fraction of the delta V that a direct ascent from Earth would require. The savings are not marginal. They are dramatic. A trajectory that would otherwise cost 30 kilometers per second of brute force perpendicular delta V can be replaced by a trajectory that costs perhaps 3 or 4 kilometers per second, applied at the right moment and in the right direction near the Sun. The geometry, once again, rewards working with the gravitational landscape rather than against it. The catch is that the maneuver requires the spacecraft to survive the thermal environment near the Sun, which is the engineering bottleneck of the whole architecture. Near perihelion, the spacecraft is bathed in sunlight of an intensity that can melt or damage any conventional structure. The temperature on the side facing the Sun rises rapidly as the spacecraft falls inward. A specialized heat shield, of the kind already demonstrated by certain modern solar probes, is required to protect the spacecraft long enough for the perihelion burn to be performed. The thermal challenges are serious. They are also solvable. The engineering exists. It has been demonstrated. The maneuver also requires the spacecraft to be carrying fuel at the right moment and to have spent very little of that fuel getting to perihelion. Any fuel used early in the trajectory does not benefit from the deep well boost. The most efficient version of the architecture spends almost no fuel on the inward fall and saves nearly all of it for the brief perihelion burn. The Sun's gravity provides the inward acceleration for free. The spacecraft only needs to begin the fall with the right initial conditions, and the geometry does the rest. This is one of the cleanest examples in spaceflight of letting the gravitational landscape do the work and using the engine only at the moment when it counts most. Picture the trajectory in stages. The spacecraft leaves Earth and turns inward, gathering speed as it falls toward the Sun. The heat shield brightens. The Sun grows in the viewport, larger than it has ever appeared from anywhere a spacecraft has ever traveled. At perihelion, the moment of greatest peril and greatest opportunity, the engine fires for only a few minutes. The burn is brief because the geometry is so favorable that only a short burst is needed to redirect the trajectory. Then the spacecraft is rising again, but now rising along a path that no straight ascent could ever have produced. The trajectory carries it out of the plane, climbing toward the polar regions of the Sun on an orbit that uses none of the brute force delta V that would otherwise have been required. There is another path out of the plane, and it carries no fuel at all. A solar sail is a vast, thin, mirror-like surface that catches the gentle pressure of sunlight itself. Each photon of sunlight that strikes the sail and reflects away imparts a tiny amount of momentum to the sail. The pressure of any single photon is unimaginably small. Integrated over a sail surface measured in thousands of square meters, integrated over months and years of continuous exposure, the cumulative momentum transferred becomes meaningful, and the sailcraft can change its trajectory significantly without burning any fuel. A sailcraft can spiral inward or outward continuously, tilting itself to use sunlight pressure the way a sailing ship tilts to use the wind. By orienting the sail at different angles relative to the Sun, the spacecraft can choose whether to add energy to its orbit, subtract energy, or tilt the orbit's plane. The choices are limited compared to a chemical rocket, because the available thrust direction depends on the position of the Sun and the orientation of the sail. But within those limitations, a sail can perform maneuvers that no chemical mission could afford, simply by letting the slow, steady push of sunlight accumulate over time. Practical solar sails for serious interplanetary maneuvering require surface areas measured in thousands of square meters. The sail material itself is extraordinarily thin films, just a few microns thick, kilometers of unfolded edge, stowed compactly for launch and deployed in space using carefully engineered deployment mechanisms. The technology has been demonstrated on small experimental missions, and the engineering is well within the capabilities of modern spaceflight. What has been missing is the funding and political will to build a sailcraft at the scale needed for serious solar polar missions. Proposed sail-driven missions to the Sun's poles have been studied under various concepts for decades. A solar polar imaging mission, in which a sailcraft spirals inward and gradually raises its orbital inclination using continuous sunlight pressure, has been a long-standing proposal in solar physics. A high-inclination solar mission concept with similar architecture has been worked out in considerable detail. Both concepts would use the patient, steady force of sunlight to do what a chemical rocket could not afford to do in delta V terms. Neither has yet been built. The fundamental advantage of a sailcraft is that it does not run out of fuel. As long as the sun shines, the sail has thrust. Mission lifetimes are limited only by the sail's durability and the spacecraft's electronics, not by the consumption of any finite propellant. A sail-driven mission to the Sun's poles could, in principle, climb to a polar orbit, observe the poles for years, and continue to maneuver as the mission required, without ever exhausting its capability to move. The economic and operational implications of fuel-free maneuvering are profound, even though the development costs of building a working sail at the necessary scale are substantial. The fundamental disadvantage of a sailcraft is that the thrust is small. Mission designers must accept that a sail-driven trajectory to the Sun's poles takes years longer than a perihelion burn trajectory would. The maneuvers are gentle. The orbit shapes itself slowly. A mission patient enough to wait out a multi-year spiral can use the sail to reach destinations that no chemical mission could afford, but the wait is real. Time becomes the trade for fuel. The most promising recent proposals combine the two techniques. A sailcraft, deployed from Earth, uses sunlight pressure to spiral inward toward the Sun without burning any fuel. As the sailcraft approaches perihelion, the sail furls or is jettisoned, and a small high-energy stage performs a solar perihelion burn at the moment of closest approach. The resulting trajectory climbs steeply out of the plane and into a polar orbit around the Sun. The combined architecture trades engineering complexity 2 propulsion regimes, 2 thermal environments, a careful handoff between them for a dramatic reduction in the total delta-V cost compared to either approach used alone. In effect, the sail does the cheap, slow work of getting the spacecraft into position near the Sun, and the perihelion burn does the brief, decisive work of throwing it out of the plane. The architecture combines the long-haul efficiency of solar sailing with the impulsive efficiency of deep-well rocketry. The result is a mission profile that no chemical rocket alone could afford, and that no sail alone could complete in a reasonable time. The whole becomes more capable than the sum of its parts, in the way that good engineering often does. Variants of the combined architecture have been studied for decades. Mission concepts have been proposed, refined, modeled, and shelved repeatedly, waiting for the right combination of scientific priority, available funding, and political timing to bring one of them to flight. None has yet been built. The missions remain on the long list of beautiful ideas in spaceflight that have been worked out on paper, tested in component-level demonstrations, and never assembled into the full vehicles their designers imagined. Other propulsion concepts could also support out-of-plane missions, given enough development time. Ion engines, which use electrical power to accelerate ionized propellant to extremely high exhaust speeds, are far more efficient than chemical rockets in terms of delta-V per kilogram of fuel, and they have already been used on several interplanetary missions to perform maneuvers that chemical rockets could not have afforded. An ion engine spacecraft, given enough power and enough time, could, in principle, perform the gradual inclination changes needed to climb out of the plane without resorting to either a planetary flyby or a deep well burn. The thrust is small, but it is continuous, and over years of operation, a small, continuous thrust can accomplish enormous total changes in velocity. Nuclear electric propulsion, in which a small nuclear power source provides the electricity for high-efficiency electric thrusters, could provide even more capable out-of-plane missions. The power available from a nuclear source is far greater than what solar panels can provide, especially at distances from the Sun, where sunlight is dim. With enough power and enough patience, a nuclear electric spacecraft could climb out of the plane, hover above a pole, observe for years, and maneuver freely throughout the mission. The technology has been studied in detail. It has not been flown at the scale that would be needed for such a mission. The choice among these architectures, when a polar solar mission is eventually funded, will depend on a great many considerations of cost, schedule, scientific priorities, and political timing. The point of tonight's part is not to advocate for any particular approach. The point is only to make clear that the missions are possible. The geometry of the solar system is not a final barrier. The delta-V wall can be climbed by clever use of gravity, of sunlight, of well-timed burns near the Sun, of the long, patient acceleration that ion engines and sails can provide. The polar regions of the Sun are not beyond reach. They are simply beyond the reach of the kinds of missions we have so far chosen to build. The principle of falling first in order to climb afterward is the unifying idea of this part. It is the gentle reminder that the universe rewards working with the gravitational landscape rather than against it. The same principle that flattens protoplanetary disks, that keeps planets in their orbits, that traps every spacecraft in the sideways flow of the ecliptic, also offers the path out of that flow, given the patience to find the right place to push. The deep well is not only the obstacle, it is also the lever. Used at the right moment, in the right direction, with the right preparation, the Sun's own gravity can deliver a spacecraft to a vantage point that no straight ascent could ever afford. Suppose, for the length of tonight's final part, that such a mission has been built. Suppose the architecture has been chosen, The spacecraft has been assembled, the trajectory has been flown, and the spacecraft has finally reached a vantage point above the Sun's North Pole or below its South Pole at a comfortable distance, in a slow, patient orbit that allows continuous observation. The instruments are functioning. The communications link is stable. The mission has begun. What would the spacecraft see? The first change is the sky itself. From inside the ecliptic, the night sky is washed faintly by the zodiacal glow sunlight, scattered by the dust that hugs the plane of the planets. The glow is gentle, but it is everywhere along the ecliptic, and it limits the faintness of stars and galaxies that can be detected from any vantage within the plane. From above the plane, that glow lies behind and below the spacecraft, no longer scattering its sunlight into the upward-pointing field of view. The sky overhead would be cleaner than any view obtainable from inside the solar system. Distant stars, faint galaxies, the cosmic microwave background, the imprint of the early universe, all would be seen against a darker, less obscured backdrop. The implications for observational astronomy from such a vantage point would be substantial. Telescopes searching for biosignatures in the atmospheres of distant exoplanets are limited, on Earth and in low Earth orbit, by scattered light from the zodiacal cloud. The cloud's glow forms an unavoidable background that competes with the faint light from distant planetary atmospheres. A polar vantage telescope would look out through one of the clearest possible windows in the inner solar system, with the zodiacal contamination dramatically reduced. The faintest signals from distant worlds would become easier to extract from the cleaner background. Measurements of the cosmic microwave background, the faint relic radiation of the universe's first moments, are similarly affected by foreground emission from solar system dust. A polar vantage would reduce that foreground significantly, allowing more precise mapping of the microwave background's small temperature variations. The microwave background carries information about the conditions of the universe shortly after its earliest moments, and the precision with which those small variations can be measured limits how confidently astronomers can reconstruct the universe's history. A cleaner sky helps with this work in ways that improve nearly every kind of cosmological measurement. Even ordinary astronomy would benefit. Variable stars, pulsar timing measurements, the long-duration monitoring of faint sources, all of these would improve with the darker, less obscured sky available from above the plane. Time domain astronomy, which depends on the ability to detect small changes in the brightness of distant objects across long stretches of time, would gain from the reduced, scattered light. The polar vantage is not just useful for solar physics. It is a uniquely clean platform for observations of the rest of the universe. The local environment around the spacecraft itself would also shift as it climbed out of the plane. Near the equator, a spacecraft sits inside the slow, turbulent, variable solar wind of the streamer belt. Slow plasma rising from the boundaries of equatorial structures, threaded with the rippling current sheet, varying in density and direction from hour to hour. As the spacecraft climbs to higher solar latitudes, the wind around it changes. The plasma becomes faster, smoother, and more uniform, the fast wind streaming straight out from the polar coronal hole, with less of the turbulence and variability that characterize the equatorial regions. The transition is not abrupt. It happens gradually over a range of latitudes, as the spacecraft moves out of the streamer belt and into the polar wind regime. The boundaries between the two wind regimes have their own structure, with mixed regions where fast and slow winds interact, with stream interactions where faster wind catches up to slower wind, and compression fronts form. The high-latitude transitions were mapped at low resolution by the first polar mission, and they revealed structures that had not been anticipated by the simplest models. A sustained polar mission could map those transitions in much greater detail. the energetic particle environment changes too. Cosmic rays, which are partially deflected by the heliospheric magnetic field as they travel inward from interstellar space, arrive at the spacecraft at slightly different rates and energies depending on the spacecraft's latitude. The galactic cosmic ray flux is one of the more interesting environmental signals available at high latitudes because the geometry of the heliosphere's magnetic field varies with latitude in ways that affect the cosmic ray's access to the inner solar system. A polar spacecraft, observing the cosmic ray flux across many years, would help untangle how the heliosphere modulates the galactic background. Magnetic field measurements at high latitudes would test directly the surprisingly uniform large-scale field that earlier measurements had suggested. The earlier hint was that, beyond the immediate polar regions, the radial component of the heliospheric magnetic field becomes roughly the same in every direction, smoothed by the way. Solar wind plasma carries magnetic flux outward. A sustained polar mission, measuring the field continuously across years of operation, could establish how exactly this uniformity arises and how it varies with the solar cycle. The field's geometry is one of the more elegant problems in heliospheric physics, and the polar vantage is the natural place to study it. Turning the spacecraft's instruments downward toward the plane of the planets would produce another first. The disk of the solar system would be visible, for the first time in history, in plan view. The orbits of the planets, ordinarily mapped by inference from in-plane observations, would be seen at a glance. The dust bands of the inner system, the asteroid belt, the orbits of comets, all would lie in a single great sheet below the spacecraft, illuminated by the sun behind it. The geometry of where we live would, for the first time, be visible from a vantage that could take in the whole pattern at once. Earth and the inner planets would appear as small bright points threading slowly along their orbits, the entire inner system visible in a single field of view. The position of each planet, the spacing between orbits, the relative motions, the slight tilts that distinguish one orbit from another, all would be resolved in a way that is simply not possible from any vantage within the plane. The image would be the first plan view portrait of the inner solar system as a single object. The asteroid belt would show as a faint band, slightly above and below the plane in places, but mostly settled into a flat ring between the orbits of Mars and Jupiter. The distribution of asteroids within the belt, the gaps in their distribution caused by resonant interactions with Jupiter, the larger Trojan groups that share Jupiter's orbit, all of this structure would be visible at a glance from above. The dust contributions from short-period comets and Kuiper belt objects would be resolved against a darker background than is possible from inside the disk, allowing the various sources of dust to be distinguished from one another with much greater precision. The image would be the first plan view portrait of the solar system as a single object. Such an image does not exist. It has never been taken. It cannot be taken from anywhere within the plane because the geometry of the plane forbids it. Only a vantage above or below the disk can capture the disk in its full layout, and no spacecraft has ever held such a vantage long enough to make the image. The portrait of our solar system, as a flat thing seen from above, is one of the great unfinished pictures of astronomy. Given a long-lived mission and sufficient out-of-plane travel, the spacecraft could also finally answer the open question of the heliosphere's shape. Direct measurements of the magnetic field and plasma at high latitudes, taken at varying distances from the Sun, would discriminate between the comet-shaped model and the deflated Poisson alternative. The two models predict different geometries for the boundary, different distributions of magnetic structure at high latitudes, different downwind configurations. A polar spacecraft, climbing outward through the heliosphere on its inclined orbit, would sample regions whose properties differ between the two models. If the spacecraft eventually crossed the heliospheric boundary from above or below, at any distance from the upwind nose, it would return the first measurements ever taken of the boundary outside the disk. Such a crossing would be the equivalent, for heliospheric geometry, of what the existing in-plane boundary crossings have been for the upwind direction. It would extend the in situ map of the boundary into directions that have never been sampled. Either result would be transformative for our understanding of the bubble we live inside. Confirming the comet's shape would clarify how the Sun's magnetic field shapes the bubble's downwind geometry, and how the interaction with the surrounding interstellar magnetic field allows or prevents the formation of a long tail. Confirming the croissant shape would rewrite the textbook picture entirely and would imply that the heliosphere is a more compact structure than the comet model suggested, with the boundary closer to the Sun in all directions and the magnetic pressure playing a more decisive role. Either way, the portrait of our home would finally have a clear outline drawn from direct observation rather than from inference. Look further upward, beyond the heliosphere, and the galactic sky comes into a new arrangement from the polar vantage. The plane of the Milky Way, tilted by roughly 60 degrees relative to the ecliptic, would no longer cut across the sky in the familiar way it does from Earth. It would rise as a great slanted band, with the bright bulge of the galactic center lying in a different direction than it does from inside the plane of the planets. The constellations of the southern terrestrial sky, the dark dust lanes that thread through the band of stars, the soft glow of the galactic regions, all would appear in a quite different geometric arrangement than the one familiar from Earth. The southern direction, below the Sun's south pole, opens into one of the clearer sightlines through the local bubble carved by ancient supernovae, the low-density region of interstellar space that surrounds the Sun. From this direction, the universe looks slightly farther, the foreground gas slightly thinner, the obscuring dust slightly less dense. A telescope pointed in this direction from below the Sun would have a particularly clean view out into the wider galaxy, with less of the local interstellar contamination that affects views from inside the plane. The geometry of the local bubble, the larger cavity in which the Sun is currently drifting, has its own structure. The bubble is not spherical. It is an elongated cavity carved by the explosions of nearby massive stars over the past several tens of millions of years, with chimneys extending vertically out of the galactic disk and a more complicated structure in the plane. The polar vantage, looking outward toward the galactic poles, would see the bubble's structure in directions that are difficult to observe clearly from within the plane. The cosmic microwave background itself, the faint relic radiation that fills the universe and that carries information about the conditions of the cosmos at the time the first hydrogen atoms formed, would be measured from a particularly clean vantage. The microwave background is everywhere, but foreground emission from the galaxy and from the solar system itself makes it harder to measure precisely from inside the disk. A polar vantage would reduce the solar system foreground substantially, leaving a cleaner residual signal. The detailed properties of the microwave background, its temperature variations, its polarization, the imprints left on it by the structures that formed in the early universe, would all become more precisely measurable. Even ordinary stars, viewed from above the plane, would be seen against a darker background than is available from Earth. Faint companions to nearby stars, faint exoplanets reflecting their parent star's light, faint brown dwarf companions drifting at the edges of stellar systems, all would be slightly easier to detect against a less obscured backdrop. The polar vantage is, in a sense, a slight darkness improvement to nearly every kind of astronomy that depends on detecting faint sources against a background of unwanted light. There is no photograph of the solar system from outside its plane. There is no photograph of the Sun from directly above one of its poles, taken at full resolution, in calm conditions, for long enough to study its dynamics in real time. These images do not exist yet. They are not impossible. The engineering is real. The principles are old. The trajectories have been calculated. The mission concepts have been worked out. We simply have not flown the mission. The view above the Sun is one of the most consequential vantage points in the solar system, and it is still empty, waiting for a spacecraft that has not yet been built. Every direction we have ever looked from has been a direction within the disk. Our solar system is a flat thing, and we have been observing it from inside its own flatness for the entire history of astronomy. The poles of the Sun, the top and bottom of the heliosphere, the vertical axis of the disk itself, all of it lies in a region we have visited only briefly, with 2 spacecraft, neither of which was able to do more than sample what is there. The first comprehensive view from above is still missing from our records. It is one of the few remaining gaps in the local map. It can be filled. It has not been filled. The Sun has waited 4.5 billion years for the first sustained look from above. It can wait a little longer. The mission is not impossible. The engineering exists. The trajectories have been calculated. What is missing is the funding, the political will, the patient agreement among the people who plan these things, that the vantage is worth the cost. The vantage is worth the cost. Tonight has been about why. The geometry of our home, the structure of our local star, the shape of the bubble we live inside, the appearance of the disk in plan view, the orientation of the galactic sky from above the plane, all of it depends on the one view we have not yet taken. The flatness of our solar system has shaped every photograph of the sky we have ever made. It has shaped every spacecraft trajectory ever flown. It has shaped the orbital mechanics of every mission, the geometry of every observation, the limits of what every telescope can resolve. The plane is not a mistake. It is not an obstacle to be overcome. It is the natural outcome of how a solar system, once formed, holds on to its shape. We have lived inside that shape for the entire history of our species. We will continue to live inside it. The only question, the question that has slowly worked its way through tonight's exploration, is when we will choose to look at it from somewhere outside. The Sun turns slowly, as it has always turned, at the still center of the disk. The planets orbit, as they have always orbited. The fast wind streams from the poles, as it has always streamed. The current sheet ripples outward, as it has always rippled. The heliosphere holds its shape, whatever shape it actually is, against the surrounding interstellar gas. All of this happens, has been happening, will continue to happen, whether or not anyone is watching from the directions that would let the watching be complete. The processes do not need the photograph. The photograph is for us. And so the long, quiet observation of the missing view becomes the gentle thread that ties tonight's exploration together. The plane is flat. The poles are unseen. The bubble is unmapped. The portrait of our home is unfinished. The engineering exists. The will has not yet been gathered. All of these things are true at the same time, and none of them needs urgent attention tonight. The universe is patient. The Sun is patient. The disk has held its shape for billions of years, and it will hold it for billions more. The view from above will be taken when it is taken, and the picture will be added to the record when it is finally added. Until then, the architecture waits, the trajectories wait, the spacecraft that would fly them wait. None of this requires anything from the listener. And so we let the sun rest where it always has, turning slowly at the still center of a disk that has held us for 4.5 billion years. The sky above its poles is empty for now, and the missing photograph is not a loss, but a promise, waiting patiently for the trajectories we have not yet flown. The flatness around us continues. The planets continue their gentle orbits. The wind continues its long outward flow. None of this asks anything of us tonight. Let your breathing slow. Let the long, quiet plane of the planet settle around you. Let the directions above and below the sun stay quiet, where they have always been. Sleep well, and good night.